Hello, and welcome to my video series on basic statistics. Now, 2 notes before we get going. Number 1, I will most often just use the word stats. There are fewer S's and T's crammed together in stats, and therefore I am less likely to trip over my own tongue, which happens often. Number 2, these videos are geared towards individuals who are relatively new or just need to review the basic concepts in stats. So if you have advanced study in quantitative methods, these videos are probably a bit below what you would need. Also, if you do have advanced study in quantitative methods, just keep in mind that I am simplifying some of the concepts for those who are new to the topic. So all that being said, let's go ahead and dive right in. In this video, we will be doing an introduction to the chi-square test. This is one of the most often misunderstood tests in hypothesis testing, so we're going to do a couple of things. We're going to set up a more complex problem that we will actually solve in the next video, but we'll talk about it in this video. After we talk about that data, we'll look at some graphs that help us understand that data better, and then we will actually do a simple chi-square test step by step, so you can see exactly how the numbers are calculated, which are actually fairly simple, and then how we interpret that. So let's go ahead and talk about our problem. Now again, this problem will be solved in the next video. In this video, I will actually be doing a simple example that we will then apply to this more complex problem. So we'll see this more again in part 2. So you work in the Office of Institutional Research at a small but growing regional 4-year university. Over the past 5 years, the number of undergraduate students at each level, so freshman, sophomore, junior, and senior, and then we have unclassified students, which are sometimes high school students or others, has changed. So we have had variation in our student headcount over this 5-year period. Now here are our questions. Now, even though some headcount random variation is inevitable, is that variation beyond what we would expect due to chance alone? Now, there is a lot packed into that question. I want to explain a couple of things. Just out in the world, when we count the occurrences of things, if we count an occurrence maybe today, and then we count the same thing tomorrow, and then we count the same thing the day after that and the day after that, there's going to be a natural random variation in the number that we count. So maybe I go out to a busy stoplight and I count the number of cars that go through it during a 15-minute interval, say during rush hour. Well, if I do the same thing tomorrow, I'm going to get a different number. If I do the same thing the day after that, I'm probably going to get a different number. But those numbers are probably going to be close together, even though they vary a little bit just, randomly. So what we're trying to ask here is that variation beyond what we would expect just due to the normal random chance variation? Now, what types of graphs can we use to better visualize our data? And how can a chi-square test help us rule out that variation due to chance alone? So where is the threshold by which we can say, wait a minute, that change is just beyond what we'd expect due to chance alone? So here is our student headcount. Now this is actual data, by the way. I did not make this up. So we have the years 2007 through 2011. Then we have the class levels, freshman, sophomore, junior, senior, and then we have the unclassified. And this tracks the student headcount, or enrollment, you can think of it, during the fall semester of each one of these years. So go ahead and take a look at that, and we'll talk about what we see. Well, one thing I notice is that for junior and senior, the headcount goes up quite a bit over that amount of time, and the same thing for unclassified. If I look at freshman and sophomore, it kind of goes up and down. There is no real, pattern as far as straight up or straight down. Now let's go ahead and do some graphing options so we can visualize this data better. Now, one of my credos is graphs are your friend, graphs are awesome, use more graphs. Take advantage of our ability to understand data visually. A column of numbers is one thing, but making it visual is a whole nother thing, and that can really help with your classmates or your instructor or your coworkers or your dean or whoever else you might be presenting this to. Take advantage of our ability to understand data visually. So in this problem, we're going to consider simple line graph, a stacked bar chart, a stacked percentage bar chart, a stacked area chart, a stacked percentage area chart, and then a spider or radar diagram. And we're going to talk about what each one does for us as far as interpreting or understanding our data better. So here's our simple line graph. And we have our 5 class levels over on the right-hand side, denoted by each line. Now, as you can see, if you start at the bottom, the special category seems to go up over time. The junior, which is the green line, goes up. The senior line, which is the purple, goes up over time. But then we have sophomore, which kind of goes up and down. And then the same thing for the freshman. It starts up, goes down, and comes up again, and then kind of goes down again. So when we talk about variation in our data across the years, this is what we're talking about. Now, because of the natural way enrollments work and other things in society and nature work, there's going to be some natural random variation. We cannot expect, unless we do some serious quota filling, to have the exact same enrollment every year. So we're going to have natural variation. Now, what we're trying to figure out is that variation within what we would expect by just sort of random chance alone? Now, here is a stacked bar chart, which is another way of looking at our data. So within each year, we have the number of students in each class level, and then they're stacked on top of each other. So what does this do for us, that's new? Well, it helps us see proportional enrollment. So you can see that the freshman, which is there in the blue bar, not only can we see its pattern over time, down a little bit, up, and then down a little bit, but we can also see its size relative to the other class levels. So it seems to be about twice as much as the sophomore, which is about twice as much as the junior, depending on the year you're looking at, and then senior and our special category. So it helps us see relative, in this case, enrollments, as one class level is compared to another. Now here's our stacked percentage chart. Now, of course, in this case, each class level is described by the percentage of the total enrollment it occupies for any given year. So if we look in 2007, we can see that freshmen were approximately 38% of our total undergraduate enrollment or head count. In 2008, that went down to about maybe 33%. By the time we got to 2011, we're almost all the way down to 30%. Now, of course, the entire enrollment takes up 100%. So it's all relative here again. And you can see that the special color there at the very top gets bigger. So it takes up a larger percent of our enrollment. Same thing for seniors, it appears, and juniors. And then sophomores seem to narrow in their percentage as we go across time. So this helps us look at relative percent for each year. Now here is a stacked area chart. Now this is very similar to the stacked bar chart, except we take that data and we go all the way across the graph with it. So this tells us a few things. If we look at the very top of the graph, we can see that it increases. So what we can say is that our overall head count, our overall student enrollment, increased over this time period from, in the mid 1400s up to above 1600. Now, as far as the individual bands, of course, those represent each class level. So if we look, the senior, the purple, seems to widen over time. The junior, the green, seems to widen over time. The sophomore level seems to narrow a bit, and the freshman seems to narrow a bit. So again, with this visual information, we can sort of make some ideas in our head about how this has changed over time. It seems that our freshman and sophomore enrollments went down a bit, but our junior and senior and special category enrollments went up over this time. And actually, with this university, I have a hypothesis, at least why that happened, but maybe we'll talk about that in the next video. Now here is our stacked percentage area chart, and this is very similar to our stacked percentage bar chart, where each band represents a percentage of the total. So again, you can see that overall the freshman seems to narrow as a percentage. Same thing with the sophomore percentage. And the junior, you got to look at two things here. Does it get wider and sort of its direction? So it does seem to get wider. And then same thing with the senior there in the purple and the special category there on top. So what can we say about this? Well, it seems that our freshmen and sophomores combined are taking up a smaller percentage of our overall undergraduate enrollment. And then our junior, senior, and special categories are taking up a larger percent over this time. So again, we have variation in our enrollment, but our question is it within just random chance variation, or is there something else going on? Now the last one we're going to look at is the spider diagram. And again, this is an often underused diagram that I think can be very helpful. Now of course, each grade level is represented by a different color, and in the center we can call that a hub, kind of like the hub of a wheel if you like, and then radiating out are the years. So each spoke coming out of that center is a year. So 2007, 08, 09, 2010, and 2011. Then of course we plot the number of students in each grade level along that spoke. Now what does this tell us new? Well, if you notice, as we swing around the spider diagram, as we get towards 2010 and 2011, we have like a bulge in the special, the juniors, and the seniors. So the lighter blue, the green, and the purple. And if you remember other graphs, that was apparent in our areas in stacked bars, because the juniors, the seniors, and the special category were becoming a greater part of our overall enrollment. Then if you look at the red, it doesn't change a whole lot over time. Sometimes it comes in a bit and goes back out, and comes in a bit and goes back out, but not by a whole lot. And then the blue starts way out, almost all the way to 600 students, comes back in to 500 in 2008, goes back out to the middle, stays in the middle, and then comes back in again at 2011. So it helps us sort of see bulges in our spider or radar diagram to see where our changes have been. Okay, so let's actually get to the heart of this video, and that is, what is a chi-square test? Now, first and foremost, make sure you pronounce it correctly. It is chi-square as in kite, not chi as in cheetah, not a chi-square, or chai as in chai tea. It's not chi-square, it is chi-square. So I've been in about 10 different stats classes between undergraduate and all my graduate work. Every class, every one of them, someone has said, I don't understand the chi-square, or I have a question about the chi-square. It's chi-square as in kite, so don't be that person in your class. Okay, now what does it do? It helps us understand the relationship between two categorical variables, and that's very important. They have to be categorical variables. So what do I mean by that? Well, grade level, that's one example in this case. So we have freshman, sophomore, junior, senior, and then special or unclassified. Sex, male or female, if we think of it as a binary category. Age group, so we could have, you've probably seen them. Are you in the age group 18 to 25, or 26 to 35, or 36 to 45, whatever? So those are categories if they're put in groups. Years, of course, we have years in this example, etc. So the important thing here is it has to be categorical variables. Now, chi-squares involve the frequency of events, or the count. So we're only dealing with counting things. We are counting members of these categories. We're not dealing in percents. We're not dealing in anything like that. We're dealing in frequencies, counting. Now, it helps us compare what we actually observed with what we expected. Okay? Observed versus expected. Oftentimes using population data, and I don't want to go into all that right now, but that's every member of a certain category we denote, so that's a population, or theoretical data. And actually, when we do our example, we're going to be using a theoretical data event, I guess you could say. Now, chi-squares assist us in determining the role of random chance variation between these categorical variables. So the relationship is going to change. But the question is that change within a certain limit we set that would account for just random variation? And finally, we use the chi-square distribution. Now, if that just went right over your head, do not worry. For this video, it's not important. Just know that we use it, and I put it in here just to be technically correct. And within that, we use what's called a critical value, which I'll explain here in a little bit, to accept or reject our hypothesis. Okay, so if all this talk about hypothesis and chi-square distribution, the critical values, or have your mind going in crazy directions right now, don't worry. And the example we're going to do is going to be so crystal clear step by step that you'll have it down pat. Now, let's look at our head count changes over time again. So we can see we have a couple of categories that seem to go up over time, almost in like a very flat straight line, and then we have a couple, sophomore and freshman, that kind of bounce all over the place. So we have variation, and we just want to know, are these categories, grade level and year, the variation that occurs, is it due to random chance alone, or is there something else going on in this data? Now, in this video, we're going to use a very simple experiment that's very common when talking about the chi-square, and that is the dice experiment. And I'm going to set it up maybe a little bit differently than other people have. So here is our example. Let's say I have 2 die in my hand, okay? And just in case you maybe are not familiar, die are the 6-sided squares that are often used in games, especially like gambling games. And they have 1 through 6 on each side. So let's say I have 2 die in my hand. One is fair, and the other is 1, 5, 6 loaded. And that means it favors the numbers 1, 5, and 6 due to alterations in its weight. So some people that cheat at casinos swap out the actual casino dice with weighted dice to get the numbers they want. Okay, so I give you 2 of them, and one is fair and one is loaded. Now I ask you to determine if it's the fair die or the loaded die I just gave you, and I want you to be 95% confident in your conclusion. Now, to do that, what you're going to do is, I'm going to ask you to do is, over the next 6 days, I want you to roll that die 100 times each day for a total of 600 rolls. Okay? And then record how many times each number occurs over those 600 rolls. So you're going to do 100 rolls each day for 600 for 6 days, 600 total rolls, keeping count, a frequency of how many times each number comes up. Now, let's assume okay, that the die I gave you is fair. Let's assume that. What would we expect to happen? What would we theoretically expect to happen over these 600 rolls? Now, if the die is fair, if we rolled it 600 times, and we have 6 numbers on the die, we would theoretically expect each number to come up 100 times. So 6 numbers, 600 rolls, each one has the same probability of coming up. So theoretically, we would expect 100 of each number to occur. So how are we going to state this hypothesis? And again, this is one of the more complicated slides, so just hang with me. First, we have what's called the null hypothesis, and that's represented by H sub 0. So if you've been in stats class, you've probably seen something like this. Now, our null hypothesis is that the die is fair. Then we have our alternative hypothesis, which is denoted by H sub 1. And our alternative hypothesis is that the die is not fair. Okay, so we have the null that says the die is fair. We have the alternative that says the die is not fair. Pretty straightforward. Now, what is the everyday sort of English way of saying this? Now, is the variation in our observed data simply due to chance? Or is the variation beyond what random chance should allow? Or, how far can our data vary before we have to reject the null hypothesis and conclude that the die is not fair, which is our alternative? So we're going to have some variation, but we need to know if that variation occurs within limits we set. Now, I asked you to be 95% confident, so that creates what's called a p-value of 0.05. So again, if that p-value concept kind of goes over your head, don't worry about it too much now. Another way of thinking about the p-value is, what level of tolerance are we willing to put on this variation? If our tolerance is pretty loose, we might have a p-value of 0.1, or sort of 10%. If we want the tolerance for the variation in our data to be very narrow, we want to be very strict, we might choose a p-value of 0.01 or 1%. So I've sort of picked the medium, which is 0.05, which is often the most commonly used in a lot of social science research. Okay, so degrees of freedom. Oh goodness, this is one of those concepts that gets flown around and flung around in stats classes and never gets explained, at least in my experience, very well. And guess what? I'm not going to explain it in this video either. Now, for this for this test, our degrees of freedom, DF, are simply the number of categories we have, which is 6. We have 6 numbers minus 1. Okay? So in this example, just kind of take it as it is, that our degrees of freedom are 6 minus 1, which equals 5. Now in the next video, when we have more complex categories, the degrees of freedom will be figured a bit differently. But for this example, it's just 6 minus 1, or 5. Now we have a concept called the chi-square critical value. Well, what is that? Well, the chi-square critical value is sort of the threshold. It is the point where we just have to conclude that our variation is too great to be explained by chance alone, and therefore we'd have to reject our null hypothesis over there. So the easiest way to find this actually is in Excel. Excel has a built-in function, sort of the chi-inverse, or CHIINV, and then you just give it 2 inputs. You give it your p-value, which in our case is 0.05, and then you give it your degrees of freedom, which in our case is 5. And then it spits back a value, a critical value, of 11.07. So When we do this, kind of keep that number in the back of your mind. Our threshold for our chi-square critical value is going to be 11.07. So what that means is that if our die's chi-square is greater than 11.07, then we have to reject our null hypothesis and claim that the die is not fair. The variation is just beyond what we would expect by normal random chance or normal random variation. So if we get a chi-square that's greater than 11.07, we gotta throw the null hypothesis in the garbage and just accept the alternative hypothesis, which states the die is not fair. So let's go ahead and do this step by step. Okay, so here is our expected frequency, which we talked about. Now on the right hand side is what our data actually produced. These are our actual observations. So 6 days later you come to me and say, here are my observations. So the number 1 came up 111 times, the number 2 came up 90, 3, 81, etc. And of course that adds up to 600 total rolls. So those are our observed frequencies when we actually did the experiment. So here's the first step in figuring out our chi-square. The math is very, very easy. Okay, so I know you're smart and you can do it. So let's go ahead and just do it step by step. The first step is we take our observation minus what we expected. So as you can see on the right hand side, it's simple subtraction. We take our observed, which in the first case is 111, minus our expected, which was 100 because we expected it to be a fair die. So 111 minus 100 is 11. And then we just do that all the way down that column. That's it. That's step 1. Observed minus expected. In the next step, we take that observed minus the expected and square it. That's it. So for number 1, remember we had 111 minus 100, which was 11. And then in this step, we just square it, which is 121. Then we do that for each of our numbers. So step 1 we subtract, step 2 we square it. That's it. Now in step 3, we take what we got in step 2, which was the squaring, and we divide that by what we expected, which is E. Okay? So in all of our cases we expected 100. This is actually very simple division. It's just moving the decimal place. So for the number 1, we had 121 minus 100. That's 1.21. For number 2, it's just, well, 1. And for number 3, we had 3.61. And for number 4, we had 0.04. And on down, 5 and 6. So that's step 3. Just remember, step 1 is subtraction. Step 2, we square that. And then step 3, we divide that by our expected, which in this case was 100, so it's very easy. Now in step 4, we just add all those up. So in our right-hand column, again, we had 1.21, 1, 3.61, 0.04, etc. We just add all those up. That's what the summation sign at the top of the slide means. And guess what, folks? We just did our chi-square. We're done. At least with the math part. So our chi-square value for this experiment was 12.26. Now, of course, that doesn't mean anything yet until we actually interpret it. But the chi-square value for this is 12.26. Now remember, our critical chi-square value was 11.07. Now guess what? 12.26 is greater than 11.07. So therefore, our die critical value is greater than 11.07. So we have to reject our null hypothesis, which said the die is fair, and claim that the die is in fact not fair. So we have to accept our alternative hypothesis, because our chi-square was greater than our critical chi-square based on our Excel formula. So how do we interpret that result? Now, if we actually use the APA format, which I encourage you to do, depending on your discipline, of course, what we would say is that the observed frequency of each number on the die differed significantly from what would be expected on a theoretically fair die. Now, of course, we have our chi-square, 5 is our degrees of freedom, n is the number of times we rolled the die, and that equaled 12.26. And then our p-value was 0.05. So if you were writing this in a journal, that's exactly how it would look in APA format. Now, our problem chi-square was 12.26. Our critical chi-square was 11.07, which is, therefore, our variation was too great to be explained by chance alone. Therefore, we must reject our null hypothesis, which is the die is fair, and accept H1, which was our alternative hypothesis, and say the die is not fair. So we are 95% confident that you have the loaded die in your hand. Now, I want to talk about just the effect of choosing a p-value. Remember I said the p-value is sort of how strict we're willing to be on accepting random variation. If we change the p-value, we're going to sort of change the threshold of what we're willing to accept as random chance. Now this is the same slide, I just changed a few numbers. So null hypothesis is still the die is fair. Alternative is the die is not fair. Same interpretation, okay? We're talking about variation here. Now here's what we changed. Instead of being 95% confident, I want you to be 99% confident. So we're going to have a p-value, not 0.05, but now it's going to be 0.01. So we're going to be much more strict on interpreting our variation. Now, what that means is that we're going to need a lot more variation in our observations in order to reject our null hypothesis. We're going to need much more variation in our observations to reject our null hypothesis because we've selected a much more strict p-value. Now, degrees of freedom are the same. Now, for the chi-square, we changed our p-value, so we're going to have a new critical value. So when we put this into Excel, we change that to 0.01. Degrees of freedom are 5. Now, our critical value is 15.09. Remember, last time it was a little bit over 11. Now it's over 15. So you can see that it requires much more variation to go over that threshold because we've picked such a strict p-value. So therefore, if our die chi-square is greater than 15.09, then we reject our null and claim the die is not fair. So again, in APA format, we would say the observed frequency of each number on the die did not differ significantly from what we would expect on a theoretically fair die. And everything there is the same, 5 degrees of freedom, 600 rolls. Our problem chi-square was 12.26, that didn't change, but our p-value did, so we have a p of 0.01. So our problem chi-square was 12.26. Our critical chi-square with a p-value of 0.01 was now 15.09. We did not cross that threshold. Therefore, our variation was not too great to be explained by chance alone. Therefore, in this case, we have to accept our null hypothesis and conclude the die is fair. And we are 99% confident that you have the fair die. Now, wait a minute. You have the same die in your hand. But in the first case, when P was 0.05, we concluded you had the loaded die. Now, with a P of 0.01, we conclude you have the fair die. What? Now, this is my point on changing the p-value, or changing the strictness with which we are willing to explain variation. So with a p of 0.05, we did not need as much variation to overcome the critical value. As you notice, the critical value went up significantly when we changed the p to 0.01. So it's just much more strict. We have to have more variation to cross that sort of 99% confidence because we selected such a low p-value. All right, just a quick review. What is a chi-square test? Remember, it is chi-square, not chi-square or chi-square. It's chi as in kite. It helps us understand the relationship between two categorical variables. That's important. Chi-squares involve the frequency of events, the count. So in this case, we were counting the number of times each number comes up. It helps us compare what we actually observed with what we expected. Chi-squares assist us in rejecting or ruling out, to some extent, random chance variations between categorical variables. And we use the chi-square distribution, which we didn't talk about. It's not important to what we're doing, to accept or reject our hypothesis regarding random chance. Now, basically what that means there is that we were able to put into Excel our degrees of freedom and our p-value, and it generated a critical chi-square value that we had to surpass in order to reject our null. That's all that little thing means down there. Okay? So that's review. Now just a reminder, in our next video, we will actually be looking at the data we started with. So look, in this case, instead of having a die with 6 numbers on it, we have 5 class level categorizations. So freshman through unclassified. And then we have 5 years. So we have 5 grade levels and 5 years for our categories. And then we're going to try to determine, or we are going to determine, whether or not the variation present in this data can be explained just by, random chance, just the random chance that comes with enrollment. All right, so that is our in-depth introduction to the chi-square. Hopefully you learned a lot, and I look forward to seeing you again in our next video when we look at that enrollment data and a more complex example. Again, thank you very much for watching, and I look forward to seeing you again next time.